The quantum Fourier transform is central to the most important and powerful algorithms in quantum computation. It is technically a little bit involved, and therefore we have to approach it systematically. And for this we will be guided by 3 questions, namely, what is it? How can it be implemented efficiently? And what is it good for? So let us start with the question of what it is. And it is actually a very well-defined unitary operator, which acts on basis states. We call it QFT. It acts on basis states X and transforms them into a certain superposition of all the basis states. This will be a sum running over all of them. And then we have here some very specific factors. And in here we have not the bitwise product, but the normal product of these integers x and z. Now this is related to a Fourier transform simply because of these oscillatory factors here. And it is technically a little bit closer to a Fourier series than a Fourier transform, but this is simply the name that people have given to it. We are going to call this state that we obtain in this way from a computational basis state x tilde. Fourier transformations also appear at other places in quantum mechanics, and it is therefore useful to compare this incarnation to other ones. And particularly illuminating is a comparison to the momentum eigenstates for a particle moving in one dimension. So there we can write the quantum state either in terms of the position wave function, integrating over all space, or in terms of the momentum wave function, and the relation between the two is just a Fourier transform. So we obtain psi tilde of p by this scalar product between a momentum eigenstate and the wave function. And we can work this out, for instance, in position representation. Where this is just the definition of psi of x. And this is the complex conjugate of the momentum eigenstate in position representation, which itself, without this complex conjugation and in the suitably normalized form, is given by this. And one of the illuminating differences between this Fourier transformation and the one that we're interested in is that this here involves still the same quantum state. So we just express the same quantum state in 2 different ways. So this is once done in terms of position eigenstates and once done in terms of momentum eigenstates. While up here we take one state and change it into another one. So this is certainly a difference, but when we pursue this further, then we get a better understanding of these states x tilde here. So let us have a look what happens when we apply this quantum Fourier transformation to the following superposition of states. A very general one, where just because of the context I'm going to denote these coefficients here, which are complex numbers, as a function of x and not as some amplitude psi x. And then we use this definition here in its first version, and then we encounter a double sum, and we are going to bring the sum over z to the front, and here we are going to collect a few terms, namely the sum over x, f of x, and these factors here. And what we have here are now the conventional expansion coefficients of a discrete Fourier series. I'm going to denote this as f tilde of z. And on the other hand, we can also write our original expression by just applying this Fourier transformation on the states x as this sum here. And now we have indeed written the same state in two different ways. Once in terms of this function here with these basis states, and once in terms of this function here with these basis states. So on this level we can indeed draw an analogy. Now this discrete version of a Fourier transform is one of the most important computational tools that we have. It has applications across all disciplines in science and technology, and even in finance and psychology and beyond. Indeed, it is so important that people have invested a lot of time to make it as efficient as possible. And indeed, this can be evaluated by something which is known the fast Fourier transformation. And in there you will need of the order of 2 to the n steps in order to get from the function f of x to the function f tilde of z. So this is a very efficient way to carry the Fourier transform out on a classical computer, and it mainly relies on the fact that these exponential factors have very systematic exponents that you can pull apart according to the common rule that e to the a plus b is equal to e to the a times e to the b. But using superpositions, we can accelerate this significantly. So on a quantum computer, we can implement this much more efficiently, namely in terms of n squared steps. And this is a really significant speedup. It is even more dramatic than what we had in the Grover algorithm, as long as n is large enough, but this is of course what we are interested in. So for instance, when we have 10 bits, then we compare 2 to the 10, which is round about 1000, to 10 to the 2, which is 100. Well, this is already some speedup, but not yet that dramatic, and it is even less than what we had in our example for the Grover algorithm. But when we then go to 20 bits, we compare round about 1,000,000 to 20 squared, which is 400. Well, modern computers, for instance, work with 64 bits. And now 2 to the 64 is round about 10 to the 19. So let's try to write this down. And this we then compare with 64 squared, which is 4096. And there the speedup is then already astronomical. But for encryption on the internet, say using the RSA protocol, you use even more bits of the order of this range typically nowadays. And I'm not going to write down these numbers. So let us turn to the how. Well, what is the secret behind all of this? Well, it is the fact that these states x tilde here are still separable states. They can be written as products of states that I call Zn-1, Zn-2 up till Z0. And these are of the following specific form. The state Zn is a superposition between the states 0 and 1 with a factor which is related to the factors that we encounter in the discrete Fourier transform, namely this factor here. And this works out because what we here really encode is our binary representation, very similar to what we had when we applied the Hadamard gate to basis states. But now this multiplies out not to the bitwise product, but to the normal product. So when we multiply this out, then we always obtain a factor of this sort here whenever the corresponding bit in Z is 1. And these are then just multiplied by these factors 2 to the n. So what we use here is simply that Z in binary representation is written like this. So we have these factors 2 to the n appearing here, and only then when Zn is equal to 1. So this works out, and this is still a separable state. Well, x can also be written in this way, but let me write this with an index m, because n already appears above, but this is still running until n minus 1, capital N, and then we have this representation here. And with this we realize, when we once more look at these factors, that fewer and fewer of these binary digits, these bits here, are relevant when we increase the value of little n. So when we take 2 to the n times x and divide this by 2 to the capital N, this curly n here, then we can also write it in the following way. So this looks like this. So this is what appears in the exponent multiplied by 2 pi I. But any number e to the 2 pi I times some integer, let's say k, just gives us 1. So we can drop everything from there where n plus m is larger or equal to capital N. In other words, we only want to keep the fractional part of this. And one way to write this down is to just write down this binary number until this place here. And then we make a dot, which is like our decimal point. And then we continue until x naught. So this has exactly the same meaning as having decimal numbers with this point here, where in this direction you would get to 1/10 and the hundreds and so forth, but here we now have 1/2, 1/4, 1/8, and so forth. And we really are only interested in this part here to the right, because everything on the left does not contribute to our expressions. Okay, so these are the key features. What we now need is a quantum circuit that takes one of our computational basis states and systematically rotates all the quantum bits into these states here. And we want to do this in a hierarchical way where we exploit this structure here. Because we can start with a quantum bit corresponding to this number here and bring this quantum bit into the corresponding state. And afterwards we will no longer need this quantum bit. In the next step, we can then work on this quantum bit and replace this by this state here. This has erased our knowledge of what this value was, but again we will not need it any further. When we turn to the next quantum bit, we operate just on this bit here, and so we carry on until we have processed all of them. In the first step, when we operate on this quantum bit, we will need all the n bits in here, so there will be n operations. But in the next step, we will just have n minus 1 operations, and this continues until we just have a single operation. So the number of steps that we need will be n times n plus 1 divided by 2. So what we need is a quantum circuit that implements all these steps. And we are first going to look at the most general version of this, because this simply translates this principle into this circuit. But then we look at a specific example so that we see how this really works.